Universidad Federal Fluminense in Niterói, and who will talk about groups of diffeomorphism of germs. I don't remember the title. Please, Javier. Can you start by recalling the title of the talk? Thank you. We do not listen. Do you speak? We hear nothing.
Oh, yes.
Ah, okay.
Okay.
Thank you.
So, thank you for the invitation. It's a pleasure to be here. What I wanted to talk about a little bit is about algebraic properties of groups of local diffeomorphisms and, if possible, also of the consequence of these properties for several problems. Okay, here when I say diffeomorphism, it's always going to be holomorphic. So yeah, you can suppose that from now on that diffeomorphism is going to be holomorphic diffeomorphism. And we're going to have 3 lectures. In the first one, I would like to do a kind of introduction to try to explain what objects we are going to use, just in case these objects are not well known for everybody. And in the second and third lectures, the idea would be to give some consequences to some problems. For instance, there is a theorem of G's. We're going to talk about a couple of results of G's. One of them is that if you have a subgroup of real analytic diffeomorphisms of the sphere, and the group is nilpotent, something that I'm going to try to define today, then these 2 properties imply that the group is kind of, is not any nilpotent group. Not any nilpotent group can be realized as a group of real analytic diffeomorphisms of the sphere. What you're going to have is that the group is metabelian. Abelian would be, I'm going to explain this later, but I can start now. Abelian is simply that, okay, you know that. It's any 2 elements commute. And you can associate the derived group, and okay, I'm going to explain this better, but it's later on. But it's a condition that it's a little, you can understand this as a generalization of being abelian. The idea here is not what this means. As I say, I'm going to explain that later on. The idea is that by using these techniques, you can start with some property, for instance, for these elements, and end up with something that, together with this one, is much stronger. And we are going to say how. There are some other consequences of this result. This can be used, for instance, to study the derived series of groups of local diffeomorphisms, to study the properties of the holonomy map associated to compact leaves, to study, for instance, problems of dynamics. We are going to see a result that is that if you have, again, it doesn't matter what these concepts are now. I'm going to explain that if you have a group of local diffeomorphisms, such that every element is unipotent, if you prefer now, you can suppose that they're all tangent to the identity, that the linear part of every single one of them is the identity. and the group is non-solvable, then there are plenty of recurrent orbits, of non-discrete orbits. So again, this is going to be a result in which I'm going to explain all this with much more detail in an upcoming lecture. But the point is that from something related to the structure of the group, you can deduce something that is a dynamical property of the group. Yes, indeed, in some sense, almost every orbit is non-discrete. For instance, in the measure sense, the set of points with a non-discrete orbit is of total measure. But the idea is that you can study several problems and relate this to other points. For instance, dynamics, the study of foliations with compact leaves, and the study of the properties of the derived series, and so on. So this is more or less what I would like to talk about, very, very roughly speaking. And I would like to introduce today the objects that we are going to use in order to try to tackle these problems. Okay, so first of all, something that probably you already know. We are going to talk about groups of local diffeomorphisms. The main problem that we are going to have is that these groups don't have lots of structure. And so in order to give more structure to these groups and I don't know, a point of view, a perspective, in order to study them, what we are going to do is, for instance, considering the Zariski closure. Okay, this is going to be inspired in the theory of linear algebraic groups. The difference mainly is going to be that this theory is plays out in the finite dimensional setting. I'm going to talk a little bit about this now. And groups of local diffeomorphisms are, by nature, the group of local diffeomorphisms in infinite dimensional. So we are going to spend some time trying to understand how to go from this setting to the setting of local diffeomorphisms, and what do you actually what results you have in here, let's say foundational results of this theory, that you get also for local diffeomorphisms. So here, you have the linear group, the group of linear operators in Cn, and this is a linear algebraic group. You have n square variables. The operations are mostly algebraic. And what happens over here, because you could actually complain and say, okay, but this is, if I consider the matrices that have that are of dimension n times n, this is Cn squared, and this is going to be an open set, because it's the set of matrices with determinant, non-vanishing determinant. But this is not a big issue, because in order to you do the usual trick, which is you add a new variable that is the inverse of the determinant. You have all the n square entries of the matrices of variables, and you add a new one, which is going to be the inverse of the determinant, and you add this condition for the elements of the group. And in that way, things work. In that way, for instance, the inverse of a matrix becomes an algebraic operation, because if you remember, the formula for the inverse is the adjoint matrix, which is obviously algebraic, divided by the inverse of the determinant, which is not algebraic, but you add the inverse specifically as an algebraic variable. So with that convention, this becomes an affine algebraic group. So just to say that the working with matrices with determinant different than 0 is no problem at all. And since now this is clearly an algebraic variety, indeed an algebraic manifold with the structure of a group, we can consider, for instance, the Zariski closure of a subgroup in there. Okay. Okay. So in this situation, when we have any subgroup of the linear group, we can consider the Zariski closure, right? We can consider the set of the ideal in these variables that we have over here, the polynomials, such that restricted to B are equal to 0, and then you can consider the set of zeros associated to an ideal. Okay, the definitions that you all know. The Zariski closure is going to be this thing over here. This is the definition. Are the matrices that are going to vanish for every polynomial that annulates all elements of G, right? Okay, and in particular, we could define, actually, that a subgroup of the group of matrices is algebraic. A possible definition could be if it coincides with its Zariski closure. The Zariski closure, if I'm going to remind you, it has very good properties when you have a subgroup of the linear group. In particular, the Zariski closure of a group is also a group. It's not difficult to prove. And so you go from, it's going to associate to any subgroup of the linear group a linear algebraic group. That is going to have, in some sense, some properties that are similar. Obviously, it's going to be very different with respect to some others. Okay, so I'm going to consider here an example. Yes, just to have an example of this that we are going to generalize later on to the case of local diffeomorphisms. So that's one of the reasons because it's interesting. Consider just this matrix. Okay? It's a matrix, if you want, in Jordan normal form. And consider now the following matrix over here, which is a bunch of zeros, 1, 0, 0, minus 1 over 2, 1, 0. Right? Now, in this context, you can consider the exponential of matrices of T times B. T is going to be a complex parameter in here. So T belongs to C. It can be any complex number. And what you have, if I remember correctly, is this matrix over here. Sorry, here is T. Right? The interesting part is that the group generated by this B, the one parameter group generated by B. So the group, well, it's indeed a set. This is a group of matrices, and this group is clearly algebraic. It's given by algebraic equations. One equation is this coefficient is equal 0, another one is this coefficient equals 0, and so on. Here again, you can ask these coefficients to be 1, and then you have to ask that this coefficient, which is A31, is equal, for instance, to this one, as A21 squared minus A21 over 2, and that A21 is A3, whatever, 2. So this is going to give us a linear algebraic group, the group generated by B, the one parameter group generated by B. Why is this interesting, and why is A written over there? It's because A is the exponential of B. So A belongs to this group over here. And in particular, if A belongs to a group, the group generated by A belongs to the group induced by B, the one parameter group induced by B. And obviously, this group is not difficult to prove that it's contained in the algebraic closure of A, of the group generated in the Zariski closure of the group generated by A. What I mean is that this is not difficult to prove. Indeed, we can prove it now. You consider a polynomial in the coefficients of the matrices, of the n times n matrices, and you compose, and you suppose, obviously, that this polynomial vanishes in the group generated by A. Okay, you need that it has to vanish in all elements of the group. And once you have that, you consider the composition of this expression over here, the exponential of t times b, with p. But this expression over here is polynomial in t. It's pretty obvious. And p is polynomial, so this is going to be a polynomial in one variable. Right? This belongs to the polynomials in one complex variable. And the interesting part is that this thing vanishes for every t integer number. Because for t equal 1, you obtain a. For t equal 2, you obtain a times a, which is in this group. And so it has to be 0 when you apply p. For t equals 3, you obtain the a to the power 3, which is going to be also annihilated by p, and so on. So this is a polynomial in one variable, and that vanishes, for every integer number. So it's identically 0, right? And okay. Yes. So this implies in particular that this group is contained in the algebraic closure of the group generated by A. Now you consider closures. Obviously, the closure is going to be preserved by inclusion. Here you obtain the same, and this group over here we already said that it's algebraic, so it coincides with its closure. So that's the closure of, well, it's pretty ugly. That's going to be the closure of the group generated by A, this one parameter group. Okay, this is an example that I wanted to explain, just to fix ideas, and because it's going to appear later on, right? So this is going to happen in general. Yeah, this very, very simple example, it's going to happen Yeah. If you have, for instance, any matrix or you prefer matrix or linear operator, and you suppose that it's unipotent, I'm going to write the definition in here, is unipotent if and only if there exists some natural number such that A minus the identity is nilpotent, so such that A minus the identity to the power m is equal to 0. If you want to see this in terms of eigenvalues of A, it's just that the unique eigenvalue of A is 1. It has just one eigenvalue, it's the same. So if you have one of these unipotent elements of the linear group, no matter what, there exists a unique linear endomorphism of Cn whose exponential is equal to b. Obviously, okay, the condition that I want is this one, that the exponential of b is equal to a. So you can have plenty of b's such that the exponential is a. But if you require that b is nilpotent, so that there exists m such that b to the power m is 0, or that 0 is the unique eigenvalue, then you have uniqueness, okay? And something that happens, and it's proof essentially in the same way that for that very simple example, is that the Zariski closure of the group generated by A is still the one-parameter group induced by B. It's the group of the exponentials of B times some complex number. So, yes. So this is a very nice example in which the Zariski closure of this cyclic group is pretty simple because it's essentially C, right? And it has dimension 1, of course. It's not that difficult to indeed to calculate this matrix, so it's a very simple case. Obviously, not every closure of a cyclic group is going to have dimension 1. This is just an example, but it's an example that is going to be interesting in the following. You want to work a bit, a problem could be the following. You consider a matrix that is diagonal, right? And you calculate the Zariski closure of the cyclic group. It's a little bit more complicated than this, but there is an expression for this Zariski closure. Okay. One thing that happens with linear algebraic groups or with the Zariski closure is that these groups are obviously Lie groups because you could say, okay, but this is going to be an algebraic set that is a group. And algebraic sets are not necessarily smooth. But since it's a group, it's homogeneous. So point is regular, all points are regular. So in particular, linear algebraic groups are always Lie groups. And since an algebraic set has finitely many reducible components, it's a Lie group with finitely many connected components. Some property that we are going also to see how we can generalize for the case of local diffeomorphisms. What else you can associate, for instance, to any Zariski closed groups, any algebraic group, Lie algebra, which could be the endomorphisms. For instance, one way of seeing this is considering the endomorphisms such that the one-parameter flow, that the one-parameter group that they generate is contained in the algebraic group. This defines the Lie algebra, and you have the Lie correspondence, in particular, from all these components. The finitely many, you can consider the connected component that contains the identity element that we are going to denote like this. And the Lie correspondence is going to give that that group, the connected component of the identity, is generated by the exponential of the elements in the Lie algebra. Generated. Okay, so you have this. This is a very rough introduction to linear algebraic curves in which we are not explaining much. But the point here is not that you understand from zero, which is an algebraic group. It's comparing with what's going to happen for the case of local diffeomorphisms. Okay. So in the case of local diffeomorphisms, first of all, which is a local diffeomorphism, we are going to work. Essentially, it's going to be a diffeomorphism that is defined in a neighborhood of a fixed point. And so, yeah, we make our life easier, and we say that the point is going to be the origin of Cn. So you're going to have in here, this is going to be an open set in Cn. This is going to be also an open set in Cn. It could be in any manifold, but doesn't matter. We are going to have, in any manifold of dimension n, we are going to have diffeomorphisms. As I said, these diffeomorphisms are holomorphic, right? Such that 0 is, the origin is a fixed point. And we are interested in studying this kind of objects just from the local point of view. So we consider what it is called germs. We establish an equivalence relation, which is essentially that two elements are identified if they coincide in a small neighborhood of the origin. Okay, that's if there exists an open neighborhood, or neighborhood, doesn't matter, W of the origin, such that the restriction to B of phi is equal to the restriction of psi to W, sorry. Right? So, but essentially, it's because it's the good way of giving to this object a structure of group, because when you compose, these domains of definition get smaller and smaller, so the way of having well-defined a composition or an inverse is not caring very much about what the domain of definition is. That's just the idea. So again, we are going to explain very simple things here in this first lecture. But I think that it's interesting to say this, even if it can be considered as pretty obvious. If you have a local diffeomorphism, okay, you have some realization. You can see this as a diffeomorphism from some open neighborhood of the origin in Cn to some other neighborhood of the origin. Okay, and in particular, it's going to have n components. So you can write this by using n functions. Right? These functions that you had over here are defined also in a neighborhood of 0, is what you know. So they can be expressed, any single one of them, as a power series. And obviously, these exponents over here are greater or equal than 0. And they cannot be all of them equal to 0 because the origin is a fixed point. So all these power series have no independent term. The same thing happens for all the others, right? That's the reason we have a 1 here. It's because it's the power series associated to F1. But here we would have something similar. So you can see here why this object is infinite dimensional. You're going to have, when you write the power series expansion of your diffeomorphism at 0, it has infinitely many coefficients, right? And you can associate, here, I'm going to, because you have something like this. You can associate to something like this its linear part. Even, yeah, it's, you can say that the linear part, of course, is going to consider here just for every one of these components the terms of degree 1. Here you don't get, you don't consider any choice of the ij's, just the ones whose sum is equal to 1. So one of them is equal to 1 and the others are 0. Okay. And here the same with this power series over here. And what's going to happen is that if you have a local diffeomorphism, you have this expression, you have this power series, you have this linear map. This linear map is in the linear group because the fact that phi has an inverse, because this is a diffeomorphism, is going to imply in particular that this linear map has an inverse. So this is going to be in the linear group. And indeed, this is an if and only if. If you have a collection of n power series, obviously this series need to be convergent, otherwise this is not going to give any kind of geometrical object. The series have no independent term, and besides that, the linear part is in the linear group, then you obtain a local diffeomorphism. This part over here is just the inverse function theorem. And this is one way in which you can define, you can now extend this concept of local diffeomorphism to what is the so-called group of formal diffeomorphisms. And what's going to be a formal diffeomorphism? Is you consider all the conditions that are here, and here you have power series with no independent term, and you have here that the linear part is in the linear group that is invertible. You forget just that these power series have to converge. You consider n uples of formal power series such that they have no independent term and the linear part is invertible. So Well, it's such that phi of the origin is the origin, that's the condition in the independent terms, and the linear part belongs to the linear group. And this gives you a group that we are going to use a lot because it's very useful for the constructions, and it's in particular the proper place in which it leaves the Zariski closure of a group of local diffeomorphisms. Okay? You can play the same game with vector fields. You can consider holomorphic vector fields defined in a neighborhood of the origin such that the origin, everything is holomorphic such that the origin is a singular point. And in this way, you obtain the Lie algebra of a singular of germs of singular vector fields at the origin. Sorry. Again, you can consider just the germs. You can say that two of them coincide if they are the same in a neighborhood of 0. That's the same definition, doesn't change anything. And in that way, you can associate to any one of these germs of singular vector field, you can associate an expression which is the expression of this vector field in local coordinates. And the FJs satisfy similar properties to the ones we saw for diffeomorphisms. So for instance, that Fj is going to be a convergent power series such that vanishes in the origin because the vector fields are singular, and that's about it, right? And again, you can define formal vector fields if you relax this condition over here. If you don't demand anymore that the power series are analytic, if you consider just, you change this condition by this one, then you obtain the so-called group of the so-called Lie algebra, the so-called Lie algebra of formal vector fields. And again, it's going to be important because it's going to be the natural Lie algebra associated to the Zariski closure of the group of local diffeomorphisms. So that's it. Something that I wanted to say about the connection between vector fields and diffeomorphisms is that if you have one of these germs of singular holomorphic vector field, you can consider its one-parameter flow, right? This is the time T-map associated to X, right? You pick a point, you follow the trajectory of the vector field from time 0 to time t, the point at, for instance, for C0, you follow this trajectory from time 0 to time t, you're going to get to some other point by following the vector field during time t, and this C1 is the image of C0 by this map. It's the time t map. I think that you know that. I hope. A good question could be, okay, can we actually define these exponential, these time t maps for formal vector fields? A good way to try to do that could be actually having a formula. So we can try to get a formula for this. f here, it's going to be just a function. Okay. So in our contest, it's just a general function defined in a neighborhood of 0. You want an analytic power series. And you can use the Taylor's formula, which is just this. And I think right here. This doesn't look like Taylor formula, but if you consider functions of one variable, and you consider that f is a function of one variable, x is partial with respect to x, it's exactly Taylor's formula. This is f of x plus t, and it's Taylor's formula. So it's the same for any other general vector field. And what else we can say? This is like an operator, right? X as a vector field, it can be interpreted as an operator of functions. So x of f is going to be another function. But you can apply this operator several times. So this is just applying the operator j plus 1 times. It's just applying x to the result of applying xg times to f. Right? That's just to explain what that this means. It's interpreting x as an operator. And in that way, you can obtain an expression in coordinates for this tiny map. Why is that? Because what's going to be the first component? It's going to be the composition of this tiny map with the first component of our first coordinate. So it's going to be this. And so on. And now we use that formula. And what is just the formula that we wrote. And the interesting part is that we can generalize this formula for formal vector fields. So if you want, you can do it also by considering that, I don't know, formal vector fields are going to be operators, are derivation of the real formal power series. Okay, but this is, I think, the simpler way of seeing this. Now, by using this formula, when x is a formal power series, then the exponential of tx, the t-time map of x, is well defined, and it's a formal diffeomorphism. Right? That's the point. And those are the main objects that we are going to use in the course. I would like to say a few words about how the exponential is just, if I write just the exponential, obviously, is going to be the time one map.
Javier, don't you need that vector field is nilpotent?
No. I'm going to talk about that now, but no, you don't need that, no. You can define it anyway. Yeah, I understand the question, but no, you don't need it, no. What happens is that in the case in which the vector field is nilpotent, the situation is much easier in several aspects. But in that way, you're going to have a map from from formal vector fields to formal diffeomorphisms. One thing that happens is that this exponential over here is neither injective nor surjective. So it's not a great map in that sense. But if you restrict this to the proper subsets, it's bijective. And in particular, the proposition is that if you consider nilpotent vector fields, formal nilpotent vector fields, I'm going to define that now. Don't worry. And you consider here formal unipotent diffeomorphisms, this map is a bijection. Which is something that we were commenting at the beginning of the talk with matrices. There is a bijection given by the exponential between nilpotent matrices and unipotent matrices. And so what does nilpotent mean? It's going to be any formal vector field such that the first jet, the linear part that you can actually calculate considering the coefficients of degree 1 is nilpotent. It's going to be represented by a matrix, and you're going to require this matrix to be nilpotent. And unipotent means that the linear part is unipotent. It's going to be the set of unipotent formal diffeomorphisms is the set of formal diffeomorphisms such that the first jet that we already saw that it's a linear operator is indeed a unipotent linear operator. So this gives a bijection, and this bijection is very nice. I mean, if you fix a jet, to fix what happens on a jet, you just need to consider finitely many terms in this expression, and it's much simpler than the general case. But the exponential can be defined in any case. Okay. One of the ideas to try to generalize the theory that we are considering for linear algebraic groups to the case of local diffeomorphisms is somehow trying to make sense of this, the k-jet of a local diffeomorphism or formal diffeomorphism, and to see this as a linear group somehow. So we are going to consider the maximal ideal of the ring of formal power series in n variables, and given a diffeomorphism or a formal diffeomorphism, we want to consider its k-jet, something that essentially feels like the k-jet. So we are going to associate phi k, which is going to depend just on the coefficients of degree less or equal than k. And it's going to be an element of the linear group associated to the following finite dimensional space, which is the maximal ideal divided by its power k plus 1. This, you are actually killing all the terms of degree k or greater. That's the reason this is going to be a finite dimensional complex vector space. We're not going to calculate the dimension. And what's the phi k? Because that's to be defined yet. You associate to the class of some element in the maximal ideal the composition. You're going to see diffeomorphisms as operators acting on functions. And this works. And this, the point here is if two diffeomorphisms coincide till level k, I mean, I don't know if it's, I think it's, yeah, long time ago. But if you have that all the coefficients of the Taylor series expansion of degree k or less than k are equal, the maps associated, the phi k's associated to these two are the same because you are killing what happens in levels k plus 1 and higher. So this gives you a linear map. Obviously, it's a complex map, complex linear map, I mean. But the issue is that this set over here is not just a complex vector space. It's a complex algebra. You have a multiplication of functions. And in particular, you have that if you consider two functions, you multiply and you precompose this with phi, this is obviously this product of these compositions. So in particular, diffeomorphisms are going to induce isomorphisms of C algebras. So when you are just considering here phi k as an element of the linear group, you're losing a structure. So every phi k is going to belongs to the group of linear operators defined in that space, the quotient of m by its k plus 1 power, right? And you are going to require that the image of every product, here this is just to imply that we are considering classes, right? Because just that the image of a product is the product of the images. This is just the structure that we were missing of C algebra and morphism of C algebra. And what happens here is two things. First of all, this decay ends up being exactly, this is our definition, right? This decay ends up being the phi k consists of the phi k's associated to diffeomorphisms, right? So by adding that they are morphisms of C algebras, you get exactly the k-jets of diffeomorphisms. That's the point number one. And point number two is that the decay is a linear algebraic group. Because if you write this expression or anyone, this is of course, but if you write all those expressions, all of them are polynomial in the coefficients of L. So it's going to be algebraic. Do I have some time? Not at all.
Almost not.
Okay.
Uh,
I'm going to try to, yeah. Okay, I'm going to say a thing.
For lunch we were hungry, now they are hungry. They will be.
The one thing that I want to say, and the next day we are going to, is that you can define the Zariski closure, and maybe the next day I can start again with this, of a group of local or formal diffeomorphisms. And how would you define this by using these ideas? So that we see what we are doing and where we are actually heading. If you have a group G, whatever that is, you can consider this phi case, right? Where phi belongs to G. So that could be the group of k-jets of elements of G, just that. But now the GK is contained in this group over here, in the DK, which is the group of all k-jets associated to any diffeomorphism. And that, the one thing that you have to remember is that it's a linear algebraic group. So you can consider the closure of the first one, which is going to be still a subgroup of DK. So these elements in the closure are going to be in there. And that, now what you do is to define the Zariski closure. You consider the formal diffeomorphisms. Here we cannot escape from this. That's the reason to introduce the formal diffeomorphisms. The theory does not work if you don't consider formal diffeomorphisms, even if you are in the analytic setting, such that you consider the projective, the inverse limit of these guys. So the formal diffeomorphisms such that phi k belongs to the closure of gk for every k greater or equal than 1, for instance. And that's it. That's going to be the Zariski closure of G. Okay, so what we are going to see the next day? Properties of this construction. Because, sure, we are actually considering jets. We are doing something kind of obvious in every level, trying to transform our operators, our diffeomorphisms, in operators that act on finite dimensional complex vector spaces. Very nice. But the point is, at some moment, we have to go back to our diffeomorphisms to the infinite dimensional case. And we are going to have that the definition that we use is the natural ones, the inverse limit. And we are going to actually see that this definition provides interesting objects.
Thank you very much. So I think we have time for quick questions. Frank, do you have any questions from your side?
Question? So first I have a question. Is it clear that the Zariski closure of GK, as you define, is also a subgroup?
Is a
Or
what?
maybe?
Sorry?
Yes. He's asking if the Zariski closure of
Yes.
a group in a linear algebraic group is a subgroup.
Yes, yes, yes. Yes, yes, because you are, I explained that not very well at the beginning, but you're doing a trick. You are considering the group of linear operators already as an algebraic manifold, and you consider closures in there, so you cannot get out of there.
So it's closed by
Okay.
by definition of Zariski closure, it's still closed by multiplication and inversion.
Yes. If you're asking if it's going
Okay.
to, if you do the closure in the naive way, if all the matrices that you get are of non-vanishing determinant, the answer is no. But we don't consider the closure in the whole set of endomorphisms. We consider it just for the linear group.
Okay, thank you. The question?
Any other question from here? Okay, if not, let's thank Javier again.